fine. Perfect. Okay, well, thank you very much for having me here. It's a real pleasure. It's a pleasure to see so many of you here. I prepared an overview of this topic that you have here in the title. So I'm very excited to tell you a little bit of a story of how these activities came about in the last many decades. So this is a long sort of history that I'll describe, I'll discuss with you. And it will touch a number of different topics. So hopefully you will find something interesting, in one or the other parts of the talk. So this will, perhaps give you a little bit of a sense of some of the challenges that we've been encountering over the years. So let me just acknowledge the fact that this is a project that has been carried out at Stanford University, but in collaboration with many other institutions. So I'll tell you a little bit about that in a moment. But the way I want to start the talk is to really tell you about the sort of the history and how this project sort of evolved over the years. As you can see, it's a long time history. Starts in the 80s. Actually, starts a little bit earlier than that. And I am an old fellow, but not that old. So this starts with other people sort of pioneering this work, and then I arrived at Stanford more or less in 2000. So that's when the timeline becomes a little bit more connected to my own research path. And one of the key elements of this entire journey is the word turbulence that you see there. So turbulence is, well, how many of you are familiar with turbulence? Do you know what turbulence is? In fluid dynamics? Well, yes. Okay. Not many of you. Well, turbulence is around us, in every possible way you can imagine. Is a way to describe motion of fluids. So, oceans, the atmosphere are fluids, and turbulence plays a very, very important role in those systems, in the analysis and the understanding of the behavior of the ocean, for example, and the behavior of the atmosphere. So turbulence is a critical element of, part of fluid mechanics. It's a critical element that requires understanding if we want to make sense of what's happening around us. So if you want to make sense of the weather patterns, or I mentioned currents in the ocean, or perhaps even climate, turbulence is a key factor. But it turns out turbulence was really difficult to study from a theoretical perspective. It was really a challenge from sort of classical mechanics to study turbulence. We know how to study fluids, we know how to study solids in a sort of a more general fashion, but turbulence sort of defeat the purpose of some of the methods that we had. And it turns out that around the 70s or the 80s, the idea of using computers to study turbulence starts to become a sort of a theme, partly because new computers were coming online that were powerful enough that could allow us to actually study some of the characteristics of turbulence that have to do with the fact that there are very, very small scales, very large scales at the same time. So you need very complex way of doing of solving a set of mathematical models to get a prediction or understanding of what turbulence is. And so that's why the time scale starts really in the 80s here. And it starts with the very first simulation of turbulence that was carried out at Stanford, at NASA and Stanford, by the fellows that you see there, Kim, Moyne, and Moser. And this is one of the first visualization of a turbulent flow simulated on a computer. Before that, you could use experiments to visualize a turbulent flow, but you couldn't use computers to do it. It was the very, very first time. So this is an historical record, actually. This movie was presented the first time in 1980 at the American Physical Society, and it was the first time that the community of fluid mechanics understood, or at least had the sense that we could use computers to represent reality in a detailed fashion. So what you're seeing here is, the flow in a channel, so between two parallel plates, is perhaps the simplest type of turbulent flow you can imagine. It's a very simple configuration to understand the physics of turbulence. So very, very simple scenario. And what you're seeing there is, imagine you have a vertical probe where you release some sort of a dye, some sort of bubbles, for example. And then you see how the bubbles propagate in the channel. And one thing you see is that they very quickly become very chaotic, right? The behavior of this bubble doesn't, it's not very simple. They don't just propagate down. They start to move around. They create very three-dimensional structures. And that's part of the challenge with turbulence, that there is sort of this chaotic nature to it. But anyway, that's sort of the start of this entire field of using computers to study turbulence. And as I said, this was very much a pioneering effort driven by the fact that computers started to become very powerful. And in that picture there, you see the computer that was used at the time. In 1972, NASA Ames, which is one of the centers that sits very, next to Stanford, received this computer, the ELIAC 4, and this computer was ahead of its time. It was a parallel computer, so it had more than one CPU. It had a very powerful memory, and actually didn't have much else. It didn't have a compiler. It didn't have tools to visualize anything. It was very, very much of a very early. At this time we're used to interfaces like this, right? Where we touch a screen. At the time, the interface were pieces of paper with holes, right? You would actually perforate these papers, and you put them in a reader in these computers. That was the interface. So it was incredibly complicated to even use. And actually, that disk that you see in front, which is meter large, is actually the hard drive. Right? So this is where you would write actually your results, your solutions, your Savior solution. There were 4 of those. They're actually coffee tables now in 4 houses in the Silicon Valley. They're really massive. So these were the type of computers they were using then. And as you can imagine now, this is 1980s. I'll quickly go through 40 years of development since, actually a little more. And computers have become many, many order of magnitude more powerful. The number that I quote there, 15 megaflops, I'll tell you a little bit more about megaflop in a moment. It's a unit of computing, how quickly you compute things, right? If you ask you, let's do a multiplication, right? It's going to take you some time to do that multiplication. That's a measure of how quickly a computer does multiplication, for example. Megaflops is thousands of floating point operations, operations that involve real numbers, 3.5 times 4.5, something like that, right? So how long a computer takes to do that is measured there, and this computer was 15 million mega per second. Okay, so that's how fast this computer was. As we will see at the end of this journey till today, we have 10, 15 order of magnitude more operations we can do per second. Okay? So you can imagine now immediately, if we were able to do this in 1980, now that we're 40 years after, if I give you a computer that is 15 order of magnitude faster, what will you compute? Right? That's sort of the perspective I want to give you very quickly here, and then tell you a little bit about why we're doing this and all of that. Okay, so as I said, I wasn't there in 1980, but I was there in the 2000 when the project switched. Oh, actually, one thing, curiosity. What you see in this corner here is the reason why this movie looks a little wobbly. The visualization capability at the time were such that to create this movie, the authors had to take pictures of a screen of steady images and then mount them together. So they actually did that, right? So you had a computer screen, you take a picture every time, and then you mount that as a movie. So it's a little wobbly because of that, right? It's really sort of the start of all we do today. Now let's just jump 20 years, and this was the kind of simulations we were doing when I arrived at Stanford. So this is a simulation. This is actually just showing a detail of a simulation is the combustion chamber of a jet engine. It's a Pratt & Whitney jet engine, one that was at the time a very popular engine that you'd see on a commercial airplane. And what you see there is the development of the temperature field, the turbulent temperature field within one of these combustion chambers. Is a reacting flow calculation, so you can imagine it's combustion, right? So you have fuel and oxidizer that burn. And as you can see, there is turbulence, right? Once again, there is very, very complex fluid motion. White is hot, black is cold in this case. And the other thing you notice is that now we are talking about a very complex geometry. Rather than just two parallel plates and a flow through it, now we're talking about fluid coming all over the place. There are holes. This is a very complex three-dimensional geometry and so on and so forth. So this project actually took about 10 years at Stanford to get to the point where we were able to do these simulations. And again, I want to point out to the computer on the left there. So you see that we moved to teraflops, right? It was megaflops before. Tera is 1,000 times more than that in about 10 years. And the other thing that is interesting here, the computer now has 8,000 CPUs. Right? Before it was something like 60, now we're talking about 8,000. So you have 8,000 units of compute that you have to use together to be able to achieve these kind of calculations. So this was, again, the state of the art at the time in 2000. Then we moved to a new project, and actually I should mention, this project, you see the name ASC program. ASC stands for Advanced Simulation and Computing, which is the title of the talk that I gave you, right? This was the actual program that the Department of Energy funded at Stanford, and where we simply started to really think about simulations in a different way. So I'll tell you much more about the program, but that's just to give you a sense that this is really where the story starts. Then after that, we moved to another engine, but in this case, it was a high-speed engine. This is an hypersonic vehicle, and the engine that propels an hypersonic vehicle is called a scramjet. This, in this case, is very high-speed air coming into a chamber, and you inject fluid, in this case, fuel, in this case, hydrogen, in the stream, and you see sort of that behavior. These are various quantities to show, again, the fact that now we have a very complex turbulent flow, very complex dynamics of the problem, combustion, and so on and so forth. Again, just to point you to the computer we were using at the time, this is now Titan. It was the top supercomputer for many, many years in the United States. And we went from tera to peta. So again, another 1,000, speed in terms of the jump in terms of speed of computing, right? So every about 5 years or so now, we're seeing this sort of jump 1,000 times faster. And 1,000 times for computer speed is an enormous amount. I mean, if you had the same for other type of technology, that every 6-7 years you have 1,000 times more performance, I mean, the world will be very different, right? Transportation will be very different, energy use will be very different. So computers have had an incredible growth in terms of performance that no other technology has had. But this is a clear example of that. And in fact, as you can see, a lot of things have changed since sort of the very beginning of that channel flow, turbulent flow, that channel flow movie that I showed you. The simulations are much more sophisticated, the geometry are complicated, the physics of the problem is complicated, even the visualizations became much more sophisticated, much more realistic. So these are all these things that develop together with the computers. After that, the project took a spin in a different direction. So these were all propulsion-related problems, right? The jet engine, the scramjet here. The next 5 years, we worked on a problem that involved energy, renewable energy. In this case, a solar receiver. So a device that transfers energy from the sun, basically, radiative heat from the sun into heating up a fluid to use it in a thermodynamic cycle. So think of doing combustion without combustion, basically. You're heating up a fluid just using solar energy. And so in this particular case, this is a complex system that involves a turbulent flow, radiation, and particles, solid particles that are actually absorbing the energy. So I'll tell you more about the movie afterwards, but as you can see, again, the complexity here has to do with the fact that the turbulence interacts with these particles, and I'll talk to you about that in a moment, because I think as a physics problem, it's a very interesting connection between the two. Once again, the computer sort of keep pace with everything we were been doing. In this case, we have Summit, which is still an active computer. It's still a very powerful computer. It's not the top one, but it's still a very, very good one. And we're talking about 200 petaflop. Okay? So this was, again, order of magnitude more than before, but it's reaching now a stage where we have sort of a transition between sort of what we call the petascale computers that for a long time was felt were sort of the target, the ceiling of what we could do. There were technological challenges of moving beyond the sort of petascale, and these challenges have to do with use of energy, cooling, other fat technology limitations that were sort of imposed on computers. But it turned out that effectively that were overcome, and today we have Frontier, which is one of the first exascale computers in the world. So we are doing now 1.5 exaflop with this machine. So again, exaflop is 1,000 petaflops, so you can sort of see the 1,000 multipliers sort of piling up in this setting. The problem we're working on, this is the actual project that I'm working on right now, is a project that has to do with rocket ignition. So we went back to propulsion, but this is now space propulsion, where we're looking at how to effectively and efficiently ignite a rocket for access to space. This is typically a second stage booster for say, SpaceX rockets. And so I'll tell you about the physics of the problem, but sort of that's the progression of this project that I wanted to start with. So now, you should ask first, the very first question of why at all we do simulations, right? I mean, these are all computer simulation of engineering devices, so why are we interested in that? And it turns out that you can think of engineering simulations as a way to really open the door to both the scientific discovery, if you're doing, say, simulations of a device that doesn't exist, that has not been built yet or has not even been designed yet, or you can think of sort of technology advances, right? You want to improve the performance of a system. Now, you can obviously do it by building prototype, testing them and improving on them, but that's expensive, slow, and potentially dangerous, right? In some cases, you might be dealing with systems that effectively could operate in unsafe conditions, explode or something like that, if you're thinking of a rocket, for example. So simulations allow you to really do a lot of that, first of all in a safe environment, but also by pushing much more the technology to understand if you can get benefits in certain ways, before even thinking about how you actually build it. So simulations are extremely valuable together with prototyping. Eventually you have to build the prototype, you have to make sure you can produce it, and so on and so forth. So there's no question that will become a critical factor in the progress, but you can do a lot of enhancement, a lot of studies, investigation directly using simulations. And so this was really the sort of backstory behind all those projects I mentioned. So I told you that most of those projects, at least starting from 2000, were part of this ASC, Advanced Simulation and Computing. So let me tell you what ASC is really. It turns out in 1995, the US Department of Energy established this program. And this is a big program for the United States. It's multiple billion of dollars that are invested every year into a program that effectively enhances the state of the art of both simulations and computing, which are two different things. I'll talk to you about that in a moment. So it turns out that the main reason why this program has been established in the United States is to really establish the use of simulation as a pillar to investigate engineering devices, various forms, scientific systems, and to basically approach what we call certification by analysis, so that you can actually test in simulation, so on a computer, an engineering device device and effectively establish if the performance are what they are, if the safety of that system is what it is, and so on and so forth. So you can actually build much more of what we can do in terms of certifying a system directly on the computer. You know that we have to do certification for all devices, auto vehicles, right, cars. You have to certify that they're safe in certain crash scenario, for example. That's a requirement of law in everywhere, right? It turns out a lot of those crash scenarios, you can test them before building machines, before building the vehicle, just on a computer. Right? And this means that if you find a flaw in the design, you find it even before you build a prototype so that you can correct it and then reduce the cost of failing the safety assessment in a real test. So this is really why this project was established in the Department of Energy. And it turns out that one of the things that the Department of Energy is doing is collaborating with universities, funding university to set up projects that are enhancing sort of the simulation and computing ecosystem in the United States. And Stanford has been partnering with the Department of Energy for the last 20 years. So these are all projects funded by the Department of Energy. Now, one thing that is interesting is that the Department of Energy doesn't necessarily care about the system I showed you, the jet engine or the solar receiver and so on. These are not necessarily problems or engineering devices that the Department of Energy cares about. What they care about are those 4 keywords or 4 items that I mentioned there. Okay, so there is a critical element. There are critical elements in these projects that are connected, that are consistent, even if we focus on a device that is different. Right? So let me unpack that for you, what those mean. So what is an overarching challenge or an overarching scientific challenge? Is a very, very specific question that you formulate with respect to a device, say the solar receiver, and this basically pushes the envelope of what we know. So for example, that solar receiver I was showing you doesn't exist, right? Nobody has built that, and it's based on a principle that is different from what is currently used in practice. And the real question is that we don't know if it works, actually. We propose to investigate if we actually can make it work, right? And so that's the scientific challenge, right? This is something that we don't know well, but we think has potential, and we want to use computations to investigate that potential. So that's the overarching scientific challenge. The second is multiphysics. Multiphysics is a keyword that doesn't perhaps make a lot of sense to you. What is multiphysics? Is the multi-universe is perhaps more common these days. Multiphysics just means that you have many physical processes that are coupled together. So I talked to you about turbulence right at the beginning. All these problems that I told you about have turbulence as a key element, but not just turbulence. So you have turbulence and combustion, turbulence and radiation, turbulence and multiphase, transport. You need to have more than just one physical process. And the reason for that is very simple. If you have one physical process, we are very good at narrowing down exactly what to do to make our life easy, right? As engineers, we tend to have a very, we're sort of built that way, that we want to simplify our life and try to find a good solution. When you start having multiple physical processes, there are a lot of conflicts, right? You might be able to do something here that simplifies your life for turbulence, but then doesn't help you with combustion, for example. And so it's a very ingenious way of getting you to make decisions about, how to build your simulations and how, the models that you use in your simulation. So that's multiphysics. The third, and obviously based on what I told you before about computers, is high-performance computing. So interestingly enough, the Department of Energy is also building those supercomputers. I told you that the project is simulation and computing, right? Simulations are the simulations I showed you. The computing has to do with using those supercomputers. And the same project is actually buying and building those massive supercomputers. And in fact, most of the budget goes into building those computers. Each one of those computers costs, $100 million, 500 million. I mean, these are incredibly expensive machines. And then you have to maintain them and so on. So this is part of the project. High performance is a key element that we have to deal with. And I want to tell you also a little bit about it. And then the final is predictive simulations. The fact that you're doing a simulation doesn't mean that that simulation is right or is correct. And in fact, these days, we can simulate anything, basically. Anything you can imagine, we simulate it. We simulate, physical phenomena, again, the climate, we simulate human body, we simulate, transmission of COVID, we simulate everything. But it doesn't mean that those models are accurate, that those results and those predictions that the models give you are accurate. Right? So how do we build an understanding of that accuracy and build confidence in the simulation? This is what predictive simulation means. That we don't just want to show that these movies are cool. We want to know that these movies are realistic, representative of the real physical processes. So that if we say this system is safe, or this system is successfully igniting, as I will show you for the rocket, we know that that's the case, that it's actually successfully igniting. Okay? So these are the keywords that sort of have these projects in common. And what I'm going to do in the rest of this talk, I'm going to give you 4 mini stories going a little bit deeper in some of these aspects. I won't go back all the way to the channel flow, so I'll start with the solar receiver, which is relatively recent at this point. And then I'll connect that to the question of prediction or understanding the accuracy. So this will go into uncertainty quantification. Then I'll take a short digression into high performance computing to tell you a little bit about the computer science that is behind these simulations, and then finish with just a short summary of what we're doing today of this project on the rocket. And I didn't mention, but if you have questions, I'm happy to answer as we go, or if, keep your question in mind and we can talk about it afterwards. Okay, so let's talk about the first, the solar receiver, the first multi-physics problems that I want to discuss with you. So again, if I told you about turbulence, so turbulence has to do with chaotic motion of a fluid. It turns out that when you have particles within a turbulent motion, things get interesting, quite interesting. Right? You can imagine that if the particles are extremely small, they will just fall. Right? In fact, that's part of the reason why pollution is so, and small particles pollution is so dangerous, right? Because it follows the air, without problems, and so you can, inhale it very, very easily, goes very, very deep down in the lungs, and so on. Now, big particles behave very differently. Big particles just don't care about the flow around them. If you launch a big particle, it's like a projectile. It just goes, independently. In fact, we talk about ballistic motion. It's just very much like a projectile. Right? But if you think about it, well, small particles behave in a certain way, large particles behave in a different way, that obviously there is somewhere in the middle where interesting things might happen, right? Where particles perhaps follow, but not always, and you can get something interesting, right? That's exactly the question that we asked. We know that there are solar receivers that operate with very large particles. Solar receivers with very small particles don't make much sense because they don't absorb any energy, right? They're just too small. You need to have surface area to absorb energy. Obviously, the large one, they work, but what about the one in the middle? Is there anything interesting that we can learn if we study particle receivers, so solar receivers with particles that are medium size? And that's sort of the start of the project. So just to give you a little bit of background, what kind of solar devices are we talking about? So you're all familiar with photovoltaic cells, right? These are not that. That's a different system. In this system, you have mirrors. So this is a field of mirrors. This is actually in the desert of New Mexico. This is a system built by the Department of Energy again, same funding system. for studying, these renewable systems. So this is how it looks like. So we have these mirrors. These are very large mirrors. So think of 2 meters by 2 meters. So very, very large. They all concentrate light onto a target. So imagine that they're all sort of operated in a way that the light concentrates on this tower. And in fact, if I turn the tower around, the target is that sort of white circle there. Now that white circle is, in scale here is about 1 meter. Right? So it's not a small, target, it's a big target. But given the concentration power of these mirrors, we have an enormous amount of energy in that circle. Enormous, 30 suns, 30 times the radiative energy that the sun has. So an enormous amount of energy. So now the question is, can we take that energy and transfer it to a fluid? Right? So that's basically how this system works. Now, as I mentioned, there are few ways to do it. One is to use perhaps a fluid that absorbs the energy directly. Now, that's good, but those fluids are nasty to work with. Very, very difficult to work with. So what we would like to use is something simple like air. Right? Air is great to use. If we can warm up air to very high temperatures, then we can use it, to extract energy afterwards in a thermodynamic cycle, as we are used to. Right? But that's difficult because air is transparent, so you cannot absorb energy directly. Right? So that's the idea of particles. Maybe we can have small particles that absorb the energy and then transfer it to a fluid. And so that's basically the idea. Every system that has been tested in this device is a particle receiver, but the particles are very large, and they're basically just falling and getting heated up, and then you use some sort of heat transfer device afterwards to extract the energy. Right? So that's the system that it was built for. So what we wanted to do is something different. We want to have small particles that are actually in a turbulent flow, and they are absorbing energy and releasing it directly, very, very quickly to the fluid. So the fluid is directly heating up as it exits this system, right? So that's the difference. In the original system, the particles get heated up. In this case, because they're small, they get heated up, but then they release the energy very quickly. So now, another thing you notice is that the particles are sort of not uniformly distributed, right? And this is what I was telling you, why this is kind of the overarching question. Can we use particles that are not following the fluid and not necessarily going independent of the fluid? These are sort of these intermediate particles. So let me tell you, what is the basic principle of particle-laden turbulence, how particles behave in turbulence. And this is sort of illustrated in this picture, here. So what happens is that if the particles have a certain size, we typically introduce the Stokes numbers, which is a way to measure the size in a non-dimensional fashion. But think of it as a size of the particle. What happens is that if you have a vortex, then the particles get centrifuged out. If you have a region of stagnation, so the flow is sort of moving in a certain direction, then the particles accumulate. And in fact, what you see in this picture are 4 jets. This is a jet sort of pointing up, and the jet is laden with particles, so you have the air jet and particles in there in a uniform fashion. And you see that when the particles are very small, the Stokes number is very small, they basically just color the motion of the turbulence. So you're basically visualizing the turbulence in this case. The particles are small enough that they just follow the flow. And it turns out this is more or less what you see in a turbulent flow, these kind of waves and so on. If they're very, very large, they just go on their own. You basically don't see the turbulence. You see, some scattering and so on, but you don't see structures and so on. What's interesting is that in the middle, especially in this region, you see some of the turbulence, but there are large regions where there are no particles. So the particles tend to concentrate preferentially in certain areas. And what is, now going back to what I was telling you, the overarching question, our question was, if we are in this regime, it means that we have a lot of small particles, relatively small, close together, right? So they actually absorb a lot of energy in a limited region of space. And And so that might be very, very efficient to then transfer that energy to the fluid. Rather than doing it, overall in a large space, but with particles that are too small, now you have particles that are close together. So you have this sort of multiplying effect of absorption and then release of energy. And that was the principle we felt perhaps we can use to build this solar energy device. I'll spare you the mathematics of it. I'll just tell you that it's a complicated problem. Actually, just write down the mathematical model. There's a lot of partial differential equations, a lot of coupling between heat transfer, fluid, and particle motion, and so on. So having said that, let me show you what happens. So before the project, what we knew was this, that if you have particles in a turbulent flow, what happens is that the exchange between fluid momentum, the motion of the air, and the motion of the particle is such that after a while, the turbulence decays. Turbulence dies with particles. It's just that the particles need energy to be moved continuously, and that energy comes from the motion of the fluid, and so you have this sort of turbulence decay, which is sort of measured experimentally here. This is actually turbulent kinetic energy, so the amount of turbulent motion as a function of how much particle concentrations you have. So as you have more and more particles, turbulence decays faster and faster. That's what we know already. And so our question was, if we move into a regime where we have radiation, right? What happens to this system? Obviously, we cannot just think about momentum, the transfer of momentum between the fluid and the particles, that is what causes that. But we have to think about this additional source of energy that comes through the particles. So the physics of the problem is much more complex. You have now an exchange of energy in addition to an exchange of momentum. And again, this is all what we wrote in the proposal. We said, suppose we have this energy, can we self-sustain this mechanism so that turbulence does not decay? We want turbulence to be sustained, otherwise this whole idea of particle concentration goes away because the flow slows down, there is no turbulence, and then the particles don't really concentrate locally anymore, right? So we want to self-sustain turbulence so that we can use this cycle over and over. And it turns out that you can actually study this on a computer, and we're able to show that turbulence actually leaves when you have radiation. So what these simulations are showing is what we call a box of turbulence, the simplest sort of scenario that you can think of, where turbulence is just in a isolated box, and you see basically particle concentration here. It starts yellow, if you remember the beginning of this movie, which is uniform concentration, and then you start seeing these purple regions that are regions where particles are very highly concentrated. And at that point, we would expect turbulence to decay, but because there is energy transfer, and so there are those waves of temperature and that gravity, density, current that are generated, turbulence is self-sustained. And in fact, the kinetic energy that is here shows that basically remains, to a certain level, doesn't decay. And so it turns out it's, we can actually keep the system going by, adding radiation. So this was very promising. And in fact, this was our first proof that the system can work. But obviously, we want to study this system in a lab, measure, the temperature increase and so on that we see, and then see if the simulations are predictive. Remember, prediction is critical here. We don't want just know that this principle can work, or this system can work in principle. We want to show that what the simulations are doing is actually accurate. It might be just wrong, right? These are just simulations. And so we built an apparatus at Stanford to study the system. I can tell you more about the apparatus, but the truth is that we measured a lot of different quantities to understand if the properties are correctly captured, the particle concentration, the temperature, and so on. We did a lot of comparison. I'll just show you this comparison of the temperature. So delta T is how much the temperature increases in a non-dimensional fashion from the inlet to the outlet. So as the fluid and the particles are moving through, we want to see if the fluid actually gets heated. We know the particles will, but we want to see how quickly we can heat the fluid, okay? Because that's what we care about eventually, of heating the air. And so these are plots that show the different level of amount of particles in the system, right? As we have more and more particles, we see more and more temperature increase, which is good. But the other thing you notice is that there is a, sort of a constant value here, but then increases near the wall. So these are the walls of our channel. The flow goes in this direction. And it turns out that the experiments and the simulation show actually quite a bit of difference here. Right? So this difference now tells us that our simulations have something different than the actual experiment. Overall, it's accurate. It's a good accuracy. It tells us quite a bit about the similarity of the experiments and simulation, but there are some obvious differences. And so at this point, the question was why we have these differences. So what is that makes the simulation different from the experiment? And it turns out that if you start looking into that, you see actually quite a bit of differences. The first is that, and it's the most interesting perhaps, is that we designed this system to use particles of a certain size, actually 11 microns. So we want the system be fed by 11 micron particles, in this case nickel particles, because their properties are right for the system we're studying. Now, in experiments, how do you do? In a simulation, it's easy, right? You just say, my particles are 11 micron. This is one of the inputs in my simulation, right? In an experiment, you can't do that. You have to go somewhere and buy those particles. Somebody has to manufacture them. And nobody can manufacture 11 micron particles. Even if you ask them, they will give you particles that in average are 11 microns, but they're not 11 microns. Some are 8, 9, 12, 15. But if you think about it in average, yes, they're 11, but they're not exactly 11, right? So that's obviously a difference, right? And if you don't account for the fact that the particles are not 11 microns, you're going to see differences, right? So that's one example, but there are many more examples. The radiation source is different in the simulation and experiments. Is again, in the simulation, you tend to make assumption that everything works in an ideal fashion, in a perfect fashion. So for radiation source, you assume that the radiation is just, going in a certain direction. We know that in general, radiation is neither, monochromatic, one frequency, or, very linear, very collimated, single direction, right? This is just because every radiation source you use has some sort of distortion in it, right? So again, thinking about all these things means that there are a number of differences, and again, there are more, but this gives you a sense of why simulations and experiments might be different. And then the question is what to do about it. We cannot enforce everything to be the same in the experiment and simulation. There are certain things that we simply cannot simulate or become too complicated to simulate. So this is where uncertainty comes into play. Right? Uncertainty quantification is a way to take those inputs and say, yes, I don't have exactly that kind of particle, but I know more or less the population side, the distribution of particles. Maybe I can account for that variability in the particles and then get my results not as if they correspond to exactly 11 micron particles, but if they correspond to the distribution of particles. And so this is what we do, and actually it turns out that your professor here, Tom Kidd, when was working with me, was actually working on this topic, on uncertainty quantification. So this is something that we've been doing for a while at Stanford, but in this case, the focus was really on, these are, the picture that you see here are actual particles, the particles that are in our experiments, right? Another thing we assume in our simulations is that they're spherical particles, because that's what you typically do. Well, they're clearly not spherical, right? So these are all things that will affect the quality of your prediction because they are different from what happens in reality. And let me just mention that typically we distinguish between uncertainties that are naturally occurring, like this, property and particle size variability. Right? These are occurring just because the manufacturing of those particles is such that there is no control. And there are a lot of other uncertainties that instead have to do with assumptions we're making. For example, we're assuming that the particles are bouncing off walls, right, in a certain way. In reality, particles might actually stick on walls. And that will obviously make a big difference in terms of the transfer, right? But I want to show you what these things are here. So this is the top picture here, is the actual powder. So these are the particles. If if you go to the manufacturer and you get the particles, this is how they look, right? It's just a powder, right? 11 micron, it's a very small particle. Then on the microscope, in the picture I was showing you before, and as a reference, this is 10 microns, right? So they are not 11 microns for sure. And the interesting thing is that this is the actual bottle that we get from the manufacturer. So this is where the particles are, the powder of the particles. And they stick on the bottle the probability distribution of the size of the particle. So it's not that they are hiding the fact that they're not 11 micron. They're actually telling you this is the distribution. There are, in average, they are 11 micron, but there are particles that are, 5 micron as well, and there is a certain probability of any particle of 5 micron. So in a sense, we knew already that there was an uncertainty in the particle size. We're simply ignoring it, right? And I think that's the key thing to keep in mind. When we do simulations, sometimes we ignore things because it's easier, but the truth is that if you want to be predictive and you want to have confidence in the result, you have to find a way to characterize that uncertainty and quantify it. So how do we do that? It turns out that computing when there are uncertainty requires a different paradigm. It's not that difficult to think about it, but it is perhaps unusual. So you start by identifying the uncertainty, as I said. You have to at least study your system and see some of, you might have a long list of things that are different, hundreds of things that are different. But that's the first step. You just have to acknowledge that these are potential differences between simulations and experiments. Then what you do is that you introduce some sort of measure that allows you to characterize those uncertainties. So for example, the particle size is something you want to characterize, but there are other things like the radiation properties of those particles. It turns out we don't have a good sense of how much absorptivity those particles have, or not precisely how much absorptivity they have, right? So this is something we need to characterize. So you have basically parameters or ranges that tell you, I don't know exactly what is the scattering coefficient of those particles, but it's in this range, right? Then at that point, what you do is that you build an ensemble simulation. So rather than running one calculation, you tend to run many of them. Each one will have different parameters. So you pick, say, one scattering coefficient for each one of the simulation. And the idea is that this ensemble then represents a population of outcomes, a population of prediction for which you can actually compute statistics. So what is the confidence in the expected value of that prediction? Now you have it in terms of statistics. So this is where, at the end you sort of build the statistical understanding. And it turns out that you can do this in many ways. And this has been sort of, my group has focused a lot on building up methods to do this. In particular, what we have been doing lately, and I'll tell you just a hint of what it is methods that allow you to do accelerated Monte Carlo. So let me, introduce Monte Carlo, the idea of Monte Carlo very easily if you haven't seen it before. Actually, you have, I guarantee you, because everybody has seen this kind of pictures. Right now, this is, a particular tropical storm in the United States. But every time there is a prediction of what happens to the storm, that's a model, right? We don't know, right? We don't have data. We don't know where the hurricane is going to go. So we have a model that predicts it. Now, if you pay attention to that, and these days it's easier to find this information, it turns out that typically you don't have one prediction. You have multiple predictions. This is actually sometimes called the spaghetti plot. And I'm Italian, so I resonate with that. So what it is that each one of the prediction here corresponds to slightly different conditions, say initial condition of the atmosphere at that time, or perhaps a different model or something like that. Now, rather than saying we just report that and then somebody has to decide what to do, what happens is that they actually compute an average of all those predictions. An average and a variance, a sort of a range, and then they produce a plot like this. Right? So when we see this kind of plot with an expected trajectory and then a sort of cone of uncertainty, that's exactly what the process is behind. Right? It's a process of running multiple models typically not just few, but hundreds of models, and then building this cone of uncertainty. And again, the idea is that this is the expected, but nobody will be surprised if it turns out that the trajectory is slightly different. Now, you also know that in many cases those predictions tend to change daily. So it's not that they're, even if in quantifying the uncertainty, that these are not exact predictions, but at least say for a day or few hours, those tend to be quite accurate, right? Then obviously the long-term prediction becomes more and more uncertain. So this is the process that they use, and the process is called Monte Carlo. So the idea is that the expected path, so if Q is the position of the hurricane in time, it's really just the average of all the model predictions, right? That's really as simple as that. That's what Monte Carlo is. That's what the statistical average means. Now it turns out that in this calculation, but in general, the problem is that the calculations are expensive. So the cost of each calculation is expensive, and you would like to run many of them so that you can do a good average, right? The error is actually, smaller and smaller if you have many repetitions of those calculations. And so the problem is that either you have a large N or you have a large C. Because if the number of simulations is very large and the cost is very large, then you quickly end up with low resources, no computational resources. Or perhaps, in the case of the hurricane, it will take you a week to do a prediction, and after a week the hurricane is gone. So that's not very useful prediction, right? So how can we, the question becomes how can you accelerate that prediction so that you can do, without a lot of resources, you can do a good job. The idea is that the error in the estimate of this expected, of this path, is actually proportional to, or inversely proportional to N. So if N is not large enough, the error in that prediction, becomes just too much, and it's not a very useful prediction. So it turns out we've been working on this for quite a while, and the basic idea is a very simple idea that goes back to annals of statistics. So some of you might be very familiar with it. It's called the control variance. And just to, I want to give you the intuition because this is what will be useful later. If you're trying to predict Q, so the position of the hurricane, you can actually build something else that is proportional to Q and to another quantity. And what is P? Well, P might be something that is easier to compute. So rather than being the trajectory of the hurricane, might be perhaps just the temperature field. Right? Not exactly the dynamics of the hurricane, but something that has to do with the temperature of velocity, the wind velocity, and so on. Now, if that's the case, it turns out that by doing a little bit of math, you can end up with an error of that estimate that is this, and if you compare it to the original one, it has this factor 1 over rho squared, right? And so if rho is actually close to 1, then this error is very small, even if n is not very large, right? Before, n had to be very large so that this error is small. In this case, if rho is close to 1, you can get a very small error with small n, which is what we want. We want to do few calculations and get a good error, a small error, right? Now, what is rho? Rho represents the correlation between P and Q. So if Q is difficult to compute, but P is easy to compute, I can do this easily, but as long as P and Q are correlated. I need to find something that correlates well, in this case, to the trajectory of the hurricane, and then I only need to compute few actual trajectories, right? Now, this is easier said than done, so the question is how you compute, a good P. In our case of the solar receiver. Well, it turns out in the solar receiver, a typical thing you can do is to use what we call coarse grid estimates. So these calculations are expensive because we have millions and millions of locations in which we are solving the partial differential equation. Actually, billions. So we have, 500 million particles and billions of grid points to do this calculation, right? That's typically what it is. So you can easily just say, okay, let's do just 1 million particles and let's do just 1 million grid points. So that's a simple way to build a predictor, right? That is that P that I was showing you before that should correlate well with the original model. Although, it's not clear if that's the case, if they correlate. And so what we do is that we actually build many what we call low fidelity models. So this is a temperature field So again, this is the system. The particles are starting cold and then get hot. This is the fluid temperature, so eventually there are some hot spots here. But this is the best simulation we can do. These are coarser simulations that are much, much faster to run. And as you can see, some of them are very different. This is incredibly different from the original one. So the question is, would this correlate well with the original one, right? And the idea is that a priori we don't know. So what we do is that we build what we call an ocean of estimators. So actually thousands of estimators, and then we optimize, we pick the ones that have best correlation with the original model. Okay, so that's the way to actually do accelerated Monte Carlo. We find what is a good predictor for performance that is coarse and quick. And without going in details, it turns out that we can do that. And what this plot shows is actually 25 models, or actually 32 low fidelity models, so 32 estimators, the high fidelity is there. And the most important thing you have to realize is that each one of these vertical bands means that the cost is going down by order of magnitude. So if I take, say, 1 hour to run the high fidelity model, which I should say is more like 1 week, but let's assume it's 1 hour, then I'm going to a tenth of an hour, 100th of an hour, 10 to the 4 of an hour, right? So this is an enormous acceleration. So I can run thousands of models here for the cost of one high fidelity simulation. So that's the way we actually build accelerated. And the idea is that some of them are actually, fairly accurate, even if they're very, very coarse. They're not truly accurate, they're only very well correlated, but that's good enough for this process. And so it turns out by doing that, we can actually build now simulations that have confidence intervals. So what I was showing you before is that, there was one simulation, one experiment, now the simulations have confidence interval, the code of uncertainty I was showing you before. And so this tells us now that we are accounting for the uncertainty in a way that is predictive. But this wouldn't be everything. The interesting thing about uncertainty modification is that it gives you more information. It's not just confidence. It gives you information of what matters. So typically we have hundreds of uncertainties, and not all of them are important. Some of them are just there, but they're not really influencing the results. Well, it turns out these methods allow you to sort of break down the uncertainty with respect to the quantity we care about, the temperature in this case, in their constituents. So it says that actually what matters is the distribution of radiation source much more than, say, the particle absorption coefficient or some of the other uncertainty. This is telling you that if you want to have results that are even less uncertain, you can actually measure better what is the distribution of radiated heat and use that in the simulation rather than assume that it's uncertain. And so it tells you how to dedicate more resources, more understanding to the problem. Okay, so let's see. I thought I was going to talk for an hour, and I'm already an hour, so I'll move quickly. I wanted to, but I don't know how many of you are interested in computer science, but I wanted to at least give you a hint of what's happening here, because it's actually quite unique. So I showed you this sort of timeline before, and I showed you some of the computers that we have been using over the years. It turns out not only computers get faster, this sort of 3 orders of magnitude every 6-7 years or so, but they have gotten very, very different over the years. So it's not that I have a program that I wrote, in 1999, and I still use it today. It's just useless now, right? So I need to adjust the way I actually do algorithms and programming as computers change. Otherwise, you wouldn't achieve performance. And so it turns out that over the last 20 years, as I said, the Department of Energy has invested a lot of effort in this. So I'm going to tell you a little bit about how we do computing in this project. The first thing, and again, you might be familiar with this, is the landscape of supercomputing. I told you what a flop is, floating point operation per second, and what an exaflop is, is 10 to the 18th of that. So that's an enormous amount of computing. And this plot shows the top supercomputer in the world. So the orange one is the performance of the top supercomputer in the world. So every time you see a sort of straight line, it means that for, in this case, 5 years, there was one supercomputer that was the top one. This is in particular, doing certain particular calculation, doesn't matter which one they are. So if you look at the orange, just now, Frontier, that just came online, has passed the threshold of 1 exabyte. Okay, so that's the top supercomputer in the world, and we are lucky enough to have access to it. Obviously, not many people have access to it, but you shouldn't really focus on that. What you should focus is the blue curve. What the blue curve is the number 500 supercomputer in the world. Okay, so this is 499 down the list from the top, right? And the reason why this is important is because, as I said, there is only one top, and it costs $100 million to operate and so on. The number 500 is likely to be in a company nearby. These are very common computers. These are not that extreme. And it turns out the trajectory is changing a little bit, but it's more or less increasing with the same rate, which means in 7 years, those computers will be 1,000 times faster, even if they're not the top supercomputers. So that's a realization that means that computing is just changing everywhere. It's not just changing in a national lab in the United States, it's changing everywhere. These things are getting 1,000 times faster every 6-7 years, right? So this is technology that is everywhere. And that's what makes it interesting to sort of think about how this computer operates, because likely in 7 years, many other computers will operate as that one. And they won't cost, an arm and a leg like that one. Okay, so the way to think of this, why is a challenge? Again, I'm Italian, so I think of this in this way, okay? So what is the difference between teraflop and then moving to, petaflop and exaflop? I will be, you don't need much to drive this thing, right, the 500. You just jump in and you drive, and actually you reach performance. Likely you push it as much as you can without any trouble. I would argue that already if you jump on this machine here, you probably can run, and get good performance, but I'm sure you'll be worried about it, right? This is not the same thing as breaking that, right? So, and also this goes fast, right? So there is perhaps some anxious behavior here. I can guarantee you if you jump in this car, it doesn't move, even if you try, right? And this is clearly much more performing than the others. So what is the difference here is not the power. The power is given, right? Somebody is telling you can drive it. What is the challenge is the user interface. It's the user interface that is completely different. The way you actually interact with the machine. In this case, it's obvious, it's trivial, Here is already a little bit, demanding. Here is absolutely crazy. And this is exactly what's happening to these computers. If you think about these computers, it's exactly the same way. You can program a laptop in a relatively easy way. If you want to extract performance from a modern laptop, it's already complicated because you have CPUs, you have GPUs, you have multiple memory banks, you have to program all these things perfectly to actually achieve performance. And it's a real nightmare for computer science students. So, the part that is really critical, and I want to give you this message if you haven't heard it, is that it turns out today computations are essentially free. If you want to compute something, you can compute it. The problem is to get the data to the unit that does the computation. When you have a machine that does 10 to 18 flops per second, right? It's okay if you do 3 times the same operation. Nobody cares, right? The important thing is that if you have to move data from very far away to that GPU, it's going to take a tremendous amount of time. You're wasting time that way. Nothing is happening until the data gets to the right point. And so I'm not going to give you the details, but we're building a system at Stanford that's called Legion, together with the computer science department, which is a new programming model that helps us building these high-performance computing simulations on these architectures. And the nice thing about the software we're building, if anybody's interested, is that we can actually write the same code basically in C++ and then run it on both CPU and GPUs without changing anything, without having to run with different programming models and so on. And these calculations are fairly large. In this case, we're using almost 20,000 CPUs, and here we're using 500 GPUs. So these are not sort of routine calculation. These are really massive calculation, and we have performance that are 90%, 85% of the peak performance. So these are extremely complex calculations. And again, Legion is an interesting programming model if you're curious about how to do that without having to learn CUDA or any other programming language that you might have heard about. So I'll finish with the final story that is the current project, just to give you a hint of what is the challenge we're dealing with right now. So as I mentioned, the project has to do with the rocket ignition. So I'll show you a video of the SpaceX main engine for the second stage. So this is what happens in reality. So take a, in a moment there will be some fuel. This is the initiation of the system, and then at some point it just bursts, right? You see this flame coming out, right? That's when the system is actually ignited. So what we are trying to do here is to build an ignition system that is novel, that uses novel technology, which is based on laser energy deposition. So the idea is that you inject some fuel and oxidizing in the chamber, and then you blast it with a laser, right? And you start to engine. So it's not a spark like in other systems or anything like that. Now, what makes it complicated is that this is in space, right? So temperatures are very low, pressures are very low. So if you mix combustion, fuel and oxidizer, they do nothing. It's just too cold to burn. So you need to inject a lot of energy locally in the right place at the right time to get this sort of burst. Okay? And let me show you our simulation. So this is how the fuel comes in. There is oxygen is black and methane is purple. And then, actually you haven't seen it, but the movie slows down, and there is a little bit of pulse of energy locally that then, boom, ignites everything. And the movie slowed down because the time scale of the energy deposition is incredibly small. It's nanoseconds compared to the flow scales, right? So we have to slow it to see it, otherwise it will look like the real movie that is just boom, eventually it just blows. Now, what is the challenge here? Well, the challenge is this. These are 8 simulations that are nominally the same amount of energy, same location, same everything. And what happens is that 6 of them ignite and 2 don't. Okay? And in this case, reliability is the key to this technology, right? If you need the rocket to ignite at a certain moment, you want that to ignite. It's not that, if it doesn't, right? You lost the rocket, right? So this is a critical thing to understand. First of all, is it true that it's so sensitive that in some cases you get no ignition? And to answer that question, again, we built an experiment at Purdue, and these are 3 rather than 8, just 3 realizations. And as you will see, the time scales are different. That's why it's a little bit slow. But you see that 2 of them ignite eventually, and 1 doesn't. Right? So there is clearly, a predictive, actually 2 ignite and 1 doesn't. There is clearly some stochasticity in the problem. It turns out that the initial condition of the system and the location of the ignition actually have a very important role to play. So just to give you an idea here, again, these are what we call probability maps. So what's happening is that now you see the jet is going this way, and we have 2 laser targets in this case, and they are only differ by millimeter, right? Y equals 7 millimeter, 6 millimeter. And as you can see, the percentage success of ignition changes enormously from 95% to 63%. So obviously, even just a small motion makes an enormous difference in reliability. The experiments show very similar answers, although even at 6 millimeter there is a much lower success here in this case. And we are working to understand how much of that is actually uncertainty. But I want to show you another thing that simulation can do for you. And actually, in some cases also experimental simulations very clearly, they can show you why some cases ignite and some cases don't, right? So let's look at why cases ignite. Now, in this case, they are actually in sync. So you see the initial deposition, and you see that it generates some sort of a structure that then eventually sort of moves towards the jet and then creates these combustion flow. it turns out the energy deposition creates an ejection of hot gases that then eventually hit the fuel and ignite the fuel. Right? That's sort of the process. It's not just energy, it's energy plus momentum that is actually helpful in this case. And so that's sort of the mechanism of initial success that we see over and over. So what is the mechanism of initial failure? Well, it's when that jet is not perfectly formed. So in this case, it's a failure. You see that actually you have hot product going both bottom and top, right? Because of fluid dynamic perturbations, the jet doesn't go down, it splits in two, and much of the hot product go away from the fuel, right? And so you don't have enough energy and momentum to actually ignite the system, right? And so this is, again, a very nice way to think of simulations, sort of not just getting the performance you want, but also understanding why. And obviously now we're working on trying to eliminate these mechanisms. So how can we make the ejection of these hot gases more robust? That's the next question. So let me conclude. I wanted to give you sort of an overview of some of these computational science projects at Stanford. And again, there are a lot of interesting things in this project. I am particularly interested in the uncertainty quantification part. And just to tell you for a moment what the research in uncertainty quantification is, as a sort of perhaps to stimulate some of you in thinking about doing graduate studies later, or perhaps getting involved in research, or perhaps even in industry when you start thinking about using simulation and how to use them properly. Well, it turns out uncertainty quantification, I think of it's sort of the prototype interdisciplinary science, right? So it has, as I mentioned, a lot of the grounds in statistics. So you need probability theory, you need statistical methods to really quantify, some of the uncertainty. So this is, some of the things I talked about. This is one of the papers, and I obviously leave you you have the recording, so you can look at this afterwards. There is quite a bit of obviously mathematical modeling that goes with it, right? We talked about the statistics for the uncertainty, but there is a lot of approximation theory that you can use, and a lot of tools from mathematics that are actually helpful. Absolutely critical is the understanding of the physics of the problem. So this is not devoid of the understanding of the engineering device that you're thinking of. So domain-specific knowledge is absolutely critical. And then final element that makes it interesting is computer science. If you can accommodate some of the elements of computer science, like using CPUs and GPUs to do uncertainty quantification, then you have an advantage and a real sort of acceleration. And so it turns out UQ sort of sits at the intersection of these four disciplines in a way that is quite unique in terms of mathematical model. It's quite unique, but not unique. It turns out sort of the broader range of overlap of this discipline is where the institute I'm the director of is actually sitting at Stanford. So ICME, the Institute for Computational Mathematical Engineering, basically is built around the intersection of this discipline. So if you're interested in research in areas related to this, you should definitely take a look at our website and think about graduate studies. Our idea is not necessarily even to stop at engineering problem. In fact, a lot of our students work on social sciences, medical sciences, and so on. And again, the idea is that these components are critical to build both modeling and also analysis of complex systems and systems that have impactful outcomes that we want to understand. So that was my advertising to that. So let me finish by showing something that maybe Tom Kidd remembers that I've used many times. As an engineer, we always think of sort of this dichotomy, right? Success and failure, obviously, right? We want to be successful, our devices should be successful, and so on. But it's clear that in studying success, you need to understand failure as well. Well, I would argue that there is an orthogonal axis to this, which is how we actually think of using technology and computations in this case to help. And I, perhaps a little bit extreme, saying that if you don't do UQ, if uncertainty quantification is not part of the picture, I would call that wishful thinking, because uncertainties are always present. all models are uncertain. Everything is uncertain anyway. Uncertainty might not matter, but it's there, right? So at least ignoring it doesn't help in my case, in my opinion. And so my message to you guys is that quadrant is where good engineering lives. Right? When you have success because you have analysis that includes your Q, that is careful with confidence, you have good engineering practice. And this is where we all would like to live. The opposite of that is negligence. Right? If you fail because you ignore things that are uncertain, you're just, it's your fault. Right? So it's a very nice dichotomy here. Right? So now the interesting question is what happens with the other two? Right? What are the other two quadrants? Well, NASA used to say that if you're there, that's not very helpful, right? And on the other end, the other quadrant is what NASA calls honorable failure. Right? It's actually, not possible to avoid failure altogether, but failure for the right reason because you have tried everything and it still fails is honorable and actually helps you perhaps improve afterwards. Okay, so I'll finish here. I want to acknowledge the most of the work that I presented is funded by the US Department of Energy, so that has been fantastic for my career and in general our understanding of these problems. And there are way too many students, postdocs, colleagues to acknowledge here, so this is sort of a general thanks to everybody that's worked on this project for the last 20 years. So thank you, I'm happy to answer questions.